going to start sharing this. What would I get if I don't know who it was that spoke out first, but what would I get if I just took a point and I divided that distance by its time? What would that give me?
An instantaneous speed.
Instantaneous speed. Okay. Any other thoughts? Everybody think it's instantaneous speed then? Lucia, you seem a bit unsure of that. Sorry, you're one of the few I can see at the top of my screen here.
I don't know. I feel like I don't know. I just feel like it's not instantaneous speed.
Isn't that acceleration? I don't know. It's not like I don't know.
All right.
Because it's in a position versus time graph. At a point, it's telling you where that object is located at that time.
Okay. Okay. All right. So let's consider this graph for just a minute. All right. We'll consider some of the things that you guys have mentioned. So one of the things that was mentioned is let's just choose a point. Okay. So this point is a position of 60 meters and time of 6 seconds. So 6 seconds, comma 60 meters. Okay. So just by knowing where it is, 60 meters from the beginning, and knowing that it took 60 seconds to get there, does that actually give me an instantaneous speed? Let's look at a different point to help clarify what I'm asking here. Let's take this point right here. Okay, right now time is 0 and the distance is, what is that, about 14? So 14, time is 0, so distance divided by time, 14 divided by 0. Oh, I'm going to infinite speed right now. Does that work? Doesn't quite work that way, does it? Okay, now if it was something like a distance versus time, possibly, if it was the distance I've traveled over that amount of time, then maybe, okay? But the way that it's given, and this is the way that you'll see graphs very often, is position versus time, okay? Now, what if I did want to find the average velocity? And somebody alluded to this earlier. They said, well, if I take 2 points, so right here at time 0, I'm at position 14, and then right here at time 6, I'm at position 60. Can I find an average speed there?
$10 meters per second.
10 meters per second, because I started at 14 and then now I'm at 60. What's the distance I traveled there, Sam? I'm glad you spoke
60.
up. Somebody had to. What?
60 meters.
No, I'm at 60 now. Where did I start at though?
Isn't it 46 meters?
I see it. You
What do you
start
see?
at 22. I mean, 12.
Yeah, each one of those squares is 2, because this is the 10 right here. And so each one of those squares is going to be 2. So I'm at 14 at the beginning. And then I go up to 60. So what is the total distance traveled there? What you got, Sam? What's our distance if we go from 14 to 60?
64 meters.
Sorry, 46 meters.
There you go. There you go. I was trying to figure out how 64 came. You just flip the numbers. Awesome. Yes. So 46 meters over the amount of time traveled, right? Over 6 seconds. So 46 over 6. And of course, we can get a number for that. 7.3 repeating meters per second. Okay. So that's the average speed. Okay, from 0 to 6. Okay, but I think it was Lucia mentioned, well, I could actually get the speed from any point to any other point by drawing a secant like this, right? A secant is just connect 2 points on the curve and then draw a straight line between them. All right. So that is the average speed. How would I change that into the average velocity? What do you think, G-Man? What's going to be the difference between average speed and average velocity here?
Average velocity is displacement over time.
Okay, good, good. What's the displacement in this first 6 seconds when I go from 14 to 60?
Isn't it the same?
Okay, so the displacement, the magnitude of the displacement is the same as the magnitude of the distance because it's always going positive, right? Okay, so how is my average velocity going to be different from my average speed? Or is it? What's the one thing that velocity would have that speed does not?
Direction.
We got to make sure that it has a direction, right? Now, you may say, well, it's already positive. Does that count? Yeah, probably, but you definitely want to be safe. And so I would always say, okay, well, to be safe, we're either going to put a plus to show that we understand that it's moving to the right, because we want to make sure that we're demonstrating the fact that we know that it has a direction. Or you could even say to the right, right? And it's not clear, but we need to have some, but right would be positive. So we'd be showing some type of connection that positive is direction to the right. But you want to make sure that you have something there demonstrating, if they're asking for average velocity, demonstrating the fact that you understand that there's direction. All right? Any questions so far? All right, so we're doing good. How are we going to get instantaneous speed or instantaneous velocity? That was coming up earlier. A couple of people mentioned that. If finding a point doesn't give us instantaneous speed, then how do I get it?
I'm pretty sure if you want to find instantaneous speed or instantaneous velocity, you take the point on the graph and then you take the two closest points like next to it on either side, and then do the same thing.
Okay, all right. So you're saying that I could just take a point, like if I wanted to know how fast I'm moving at this point, I could just take a couple of near points and then do that secant thing and say, that's probably pretty close. All right, good, good. That is certainly a way to estimate it. And obviously, the closer that these points are, the better that your estimation is going to be.
Yeah, the more accurate your actual answer will be.
Okay, good. Of course, once you get to trying to get points this close, it's going to be really hard to estimate what the values of those points are on a graph, which now leads you to more uncertainty. Okay? So that will work, and if you have nothing else, then we'll go with that. But there is one better way to do it, which is what we're going to do. That's why we're going to learn it right now. Anybody know? What do we get when we bring those two edge points, the 2 points on the side, closer and closer and closer to that point? Anybody know?
I'm not completely understanding your question.
Wouldn't you need calculus to find the exact instantaneous rate of change?
Okay, so calculus would be nice, right? But why? What does calculus find for you?
The instantaneous, like the derivative, the instantaneous rate of change.
Yeah, but what does that give you? What physically is that?
An equation.
It's an equation, but what does that what is its relationship with the graph?
A tangent line.
It is the tangent line. All right. So I'm going to, for those that don't understand that whole conversation, that's fine because you shouldn't at this point because you haven't done calculus, but this is your introduction. Okay. What we can do is we can find what's called the tangent. And so that means at that point, we do our best to draw a line that is tangent to the curve at that point. Okay, so what that means is it goes through that point and it touches the curve, just touches it. It doesn't cross it, okay, but it touches it as well as it possibly can. The slope of the line at that point is the instantaneous speed, the instantaneous velocity if you give it a direction, okay? So this is basically what was being talked about earlier. It was, who was that? Averett was talking about the 2 points, choosing a point on either side. This is a way of bringing those 2 points in as close as possible. We draw what's called a tangent line. And that tangent line, the slope of that tangent line will be the speed, the instantaneous speed at that point. Okay, so once I have that, I can choose 2 points on the line. Okay, so I can choose, for example, this point right here, which would be about 5.5, comma 46. And then I'll choose another point down here at the end, which is like 1, comma 6. And so now I'll find the slope between those 2 points. One thing that I want you to notice when I find the slope, if I keep the units in there, right? So I go final y value, which is 46 meters, minus the initial distance, which is 6 meters, divided by the final time, which will be the 5.5 seconds, minus 1 second. When I put all that together, I get 40 over 4.5, but the units are meters per second, which is the units of speed. Okay, whenever you find the tangent of a graph, the y over the x should be the units of what you get. And there are times that we may be able to get things from a graph that we didn't know that we could get. For example, the instantaneous speed by getting the tangent or finding the slope between 2 points, which would have the same thing, the m over the s. All right. What did you guys get for your instantaneous speed?
8.8 repeating meters per second.
Anybody else get that?
And then your velocity, it would be the same thing, but positive or in the right direction.
That's right. That's right. Instantaneous speed and instantaneous velocity will always be exactly the same. Okay, with the addition of a direction for the velocity. Okay, average velocity and average speed don't have to be the same. In this case, they were, but they don't have to be. But as long as it's only traveling in one direction, then those two things should be the same.
Wait, sorry, do you mind repeating that? So velocity and speed are always going to be the same.
So yeah, instantaneous speed and instantaneous velocity have to be the same, right? They both come from the slope of the graph, and that's how fast am I traveling right now. The only difference is that the instantaneous velocity will have a direction, where the instantaneous speed does not.
Okay, thank you.
Yeah. Average speed and average velocity, as you found out last night, don't have to be the same. In fact, very often, if the direction changes at all, then the average speed, average velocity will not be the same. Okay. Any questions? Okay. What I'd like to do is just draw a couple of pictures and see if we can interpret what these pictures are. All right. So follow along with me. These are going to be position, much like the one that we just saw, position versus time graphs. All right. So we're going to put position on the left-hand side, and we're going to put time on the x-axis. All right. So what we're going to do is I'm going to go ahead and draw up a picture. I'll give you 20 or 30 seconds to think about it. And then let's see. I think last time I called on Jimin, right? Jimin, can you give me a number?
5.
5. Okay. Awesome. So number 5 gets to share their thoughts with us. Okay, so here we go. Position versus time. All right, here's the first one. There you go. I want you to think about what that means. What is that telling us? You got about 15, 20 seconds. All right, Dewa, what you got?
I think that the object isn't moving. It's staying
Okay, why do you say that?
because
All right.
the position isn't increasing or decreasing, but the time is still what is called moving.
Okay, so time is passing, but the position is staying the same, therefore not moving. Okay, can we connect this with what we just did in the previous screen with the slope? What is the slope of that line there? What do you think, Dewa?
Oh, what do you mean by that?
Remember in the previous screen, we were talking about how we could use the slope of a position versus time graph to give us some information. What is the slope here?
would it be 0?
Yeah, 0, right? Because it doesn't rise. So the top of your fraction is 0. And then the run is any number you want because 0 divided by anything is 0. That's exactly right. And so we can use that interpretation of a graph, the slope, to tell us that the slope of this is 0. Therefore, the velocity is 0. The speed is 0. And it doesn't matter if you choose 2 points to get the average velocity, or if you choose a single point and put on a tangent, it's going to give you 0 no matter what. All right, awesome. Dewa, can you give me another number?
I'll go with 6.
Perfect. Okay, here's our next graph. There you go. Think about that one. All right, you, what do you think?
It's like as time passes, the position of an object is decreasing.
Okay, position is decreasing. What else can you tell us?
The slope is negative.
Okay, slope is negative. What does that mean?
Does it mean, I don't know, like directions?
Okay, yeah, so it's going in the negative direction, whatever that means in this point. If we say this is one-dimensional going to the right and left, we could say it's going to the left. All right. What else can you tell me about the slope? What does the slope give us?
It tells us that x gets smaller over time.
Okay, so the graph tells us that x gets smaller over time. Okay, good.
I think it tells you the slope of the tangent line, and then it would tell you that your velocity and speed are negative.
Okay, so velocity and speed are negative. Okay, is the velocity changing?
There's constant acceleration.
Constant acceleration? Well, I guess you could say that, but what is the acceleration here?
0. The object is not accelerating.
Why would you say that, Lucia?
Because it's a straight line, so the velocity is constant.
Okay, so if I were to do, it doesn't matter which method, whether you're finding the average speed or the instantaneous, you're going to get the same thing because it's a straight line, right? So here's my instantaneous velocity here. Here's my instantaneous velocity here. There's the tangent, right? It doesn't matter which point you look at, the velocity is always the same. Okay, so you pointed out that it was negative, which is perfect. It's negative, it's going back towards the origin or to the left or whatever it may be in this scenario. But importantly also, the magnitude of the velocity is not changing. It's always the same. And remember, acceleration is defined as the change in velocity over the change in time. And if velocity is not changing, if this velocity and that velocity are the same, final minus initial is going to give me 0. I'm going to get 0 over whatever my time is. And so acceleration is 0. So Sem said, well, the acceleration is constant. Yes, it's constant. It is constant at 0. There is no acceleration here. Because the line is a straight line, the velocity or the speed is always the same. Questions?
If we have a velocity over time graph, I don't know if that's a graph, but if it was a straight line, it would have acceleration, right? Because I remember learning something like that, but I'm not like completely sure.
We will look at that next. All right, in just a couple of minutes. We're going to do a couple more of these and then we'll look at velocity versus time. Absolutely. Cool. All right, here's another one. All right, let's see. You give me a number, my friend.
9.
Okay. So you guys know if you give a simple one-sentence answer, I'm going to start asking you more questions. So try to come up with as many details as you can, right? In the second one, we found out, oh, it is moving in the negative direction. It has a negative velocity. It has a constant velocity, which means no acceleration, right? Get as many details as you can. I'm going to give you a little bit longer on this one. All right, Sarah, what do you say?
So the position is decreasing as the time increases. And I don't know if this is the correct term, but the position is gradually decreasing as the time increases. And it's not at a constant rate, seeing as it's a curved line, and it's probably like quadratic function.
Okay. What do you mean when you say the position is decreasing?
I was mostly talking about the value, but if you seeing as it goes into like the next quadrant over here, it is probably changing direction as well. Actually, I'm not sure about that, but like the value was decreasing in the first quadrant, like getting closer to 0. So
Okay, so in the first quadrant, you're right. It's getting closer and closer to 0 because this is my 0 position.
yeah,
Awesome.
and then it increases in the other quadrant.
Okay, so what does that mean that it's increasing in the other quadrant?
It probably means there's a change in direction of the object's path. Or
So let's think about let's think about simple one-dimensional motion. Okay, we'll consider that it's moving to the left and to the right here. That's all that's happening. Okay, we're not trying to do two-dimensional or three-dimensional. Let's just say it's moving side to side. So in the beginning, what direction would you say it's going?
to the left.
Okay, so it's moving to the left. It gets to the 0 point, and then what happens?
Does it move to the right?
If it
No,
moved to the,
does it just continue moving to the left?
you got it,
Okay.
right? You got it. How do we know it keeps moving to the left?
I'm not sure.
Okay, there's two things, guys. Class, there's two things, and then we'll come back to some of the other things Sarah talked about. Okay, two things that tell us that it's moving to the left. Can anybody identify either of those?
If the position change is negative, so like say you're going from 20 and you're decreasing in position down to 0, and then also if your position is negative, like less than 0, then tell me.
Does position being negative mean that I'm moving to the left?
Yes. If you identified that negative as the left.
Okay. Any thoughts on that? Does a negative position mean that I'm moving to the left? And this is a really, really hard thing to get past.
No.
Kobe says, well, you keep asking that question. The answer must be no. Do you know why, Kobe?
Because it's relative.
What do you mean?
Like it's the direction is not always going to be left on, like, you know, on a 2D, I mean, even on a 2D graph, because it can be at different angles, I guess.
Okay, but we're not even going to worry about 2D right now. Let's just go straight up 1D. Okay, so I'm going to rearrange my setting right here. Can everybody see where the window is? Okay, this right here, the beginning of the window, is my origin. That's 0, right? Anything to the right is positive position. Anything to the left is negative position. Everybody okay with that? Okay, that's position. So when I stand right here, and I'm right here at the edge of the window, that gives me 0 position. If I'm standing over here, I now have a positive position. Does that tell you which way I'm going? Do you have any information on whether I'm going to the right or to the left based off of my position?
Yes. Because because you specified.
What do you mean?
You specified which values correlate with left and right, and so since you moved to a positive value, we know that you moved to the right.
You're saying from the beginning to that position, I moved to the right.
Right.
Okay, but what if I didn't start at the window? What if I'm just saying right now, I am to the right?
Then
Do you
no.
know which direction I'm heading in?
No, I wouldn't know what direction you are if you didn't have a frame of reference.
So what's required for that frame of reference?
The displacement?
Yeah, another point, right? You need another place in time. You need another place in time because in order to find the direction that you're traveling, you need a change in position. And a change in position over time is defined as what?
Velocity.
Velocity, isn't it? Velocity is what tells you which direction you're going. Okay, position doesn't tell you which direction you're going. I can be standing here and I can have 0 velocity even though I'm in a positive position. I could be heading in this direction, which gives me a positive position, but a negative direction. Or I could be standing here going that way, which would mean I have a positive position and a positive direction. The velocity is what tells us what direction we're going in. I can come over here now to the negative side. This is a negative position. I am to the left of my 0 line here. I have a negative position. But that doesn't tell you which direction I'm moving. If I tell you I have a positive velocity, that means now I have a positive velocity in the positive direction, because velocity is the change in my position over time. So if my change in position is positive, I'm moving in the positive direction. But if my change in position is negative, I'm moving in the negative direction. So when I look at my graph, and down here, I have a negative position, right? Because my graph is below the x-axis. What does that mean? Just the negative position. What does that mean?
It means you're to the left of the origin.
Absolutely. That's all it means. Having a negative position just means I'm to the left of the origin, right? Now, what there tells me, because Sarah said earlier, well, you're continuing to move in the same direction. Earlier, we said we were moving in the negative direction. We were starting at a positive point, moving back towards a zero. After I cross through, after this point, I continue moving in the leftward direction. What is it that says that I continue moving to the left? What about the graph says that he continues moving to the left?
The arrow on the slope.
Slope or negative.
This, right? The tangent, which gives us the instantaneous velocity. The fact that the slope is still negative there. A negative slope means a negative velocity, which means negative direction. And you'll notice that everywhere on this graph, it doesn't matter where it is, the velocity, the slope is always negative.
I have a question.
Yes.
Is it fair to say, like, is this right to say that the graph is accelerating towards a negative direction as well? Because it's getting
Dang
faster?
it. You just saved Elena. I was about to call on her.
My
Don't worry,
bad.
Elena. Your chance is coming up. Yes, that's exactly right. Was that Arya? Sorry, the picture didn't show up. Or was that Yusuf?
No, it wasn't. It was
Okay,
alright.
all right. So that was the next thing I was going to ask is if you look at these velocity vectors, right? If you look at the velocity vector, which is that it's getting steeper and steeper and steeper, right? You start with the velocity slope that's kind of like this, and then as time progresses, it gets more and more steep. What that means is that the value of the velocity is getting more and more negative. Now, if the velocity is changing, so it gets more and more negative, what does that mean about the acceleration? Remember, acceleration is defined as the change in velocity over the change in time. If the velocity keeps getting smaller and smaller, what is the acceleration? Is the acceleration positive or negative?
Negative?
Yeah, why would you say that, Elena?
I don't know. It was a guess.
Okay.
Because the velocity is increasing more and more in the negative direction. So.
Okay, because the magnitude of the velocity is increasing, but in the negative direction, right? We start off with a very, very low velocity here, right? And as we go, it gets more and more negative. The only way that the velocity can keep getting more and more negatives is if the change is negative, which means the acceleration is negative. Now, without doing some calculations, we can't find out if it's a constant acceleration or not. What we do know is that the acceleration is negative and that it is throughout, okay? Would you say that this object is speeding up or slowing down?
Speeding up,
Yeah, why, Yusuf?
because you can tell by the slope it gets, like, I'd say steeper, but I don't know if that's the correct
Yeah, it is. It is steeper, right? Steeper in a negative direction, but that's still steeper. Exactly. The value, the magnitude of the slope keeps getting bigger and bigger and bigger. So this is a good example. Okay, so the position is moving to the left. We're going to try to sum all this up. Position is moving to the left the whole time. It never changes direction. It keeps going left, 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 left. You can tell because the x values keep getting more and more and more negative, right? You can also tell because the velocity is negative. Okay? Negative velocity means it's moving to the left. Velocity tells you the direction. Position does not. Okay? Velocity is negative. Okay? The velocity is changing. We said that the acceleration is negative. We also said that it is speeding up. We got all of that from this one little dinky line that I just drew. Questions? No questions? I'm about to make it more interesting. You know what that means? That means it's gonna get more complicated. I know, Elysium. It's all right. We'll talk through it.
I keep missing
Okay.
parts of the lesson because I have to answer the door.
Yeah,
I
I
really
see
don't know
you
what's going
jumping up and
on.
down. Sorry. I've got it recorded, so you can step in and watch it again if you ever need to. Okay. All right. We're going to move along then. Sarah was mentioning this before. Because not only do we need to be able to interpret position versus time graphs, we want to be able to interpret velocity versus time graphs. All right. So here's what's going to happen. I want you guys to have a little bit of time to talk with each other on this one. Okay, so I'm going to go ahead and draw it up here. After I draw it up, you're going to have a minute that I'm going to send you out into breakout rooms to talk about it. So copy it down, because if you don't copy it down, you won't have a picture. Okay, so I'll draw it up, copy it down. I'll send you into breakout rooms. I'm going to call you back right away, but you have 1 minute, right? So that makes sure that you have 1 minute to discuss it. So don't come back right away. Come back after you've had a chance to talk about it. All right, so now we've got velocity on the y-axis, and we've got time on the x-axis. Okay? Okay, there's your graph. I'll give you a second to copy it down. I'm going to send it into breakout rooms. Okay, ready? Here we go.
Oh, I think for some reason I came back.
All right, you can chat with me then. What do you see, Yusuf?
Yeah, so at first it's a constant velocity, positive constant velocity, and then the second one would be constant velocity level.
So what does that mean?
So first it's increasing, like it's increasing at a constant velocity at first.
Increasing what?
Like the position is increasing constantly.
Okay.
And the second one is decreasing.
Waiting for everybody to come on back. Neve, can I get you to share what you guys decided is happening here?
We said that the first one is constant positive velocity and the second one is constant negative velocity.
Okay, what does that mean?
So it's traveling in the positive direction. There's no acceleration, so it's staying the same speed.
Okay, so acceleration
Velocity.
0, same speed. You said something about the positive direction, so we're going to say moving to the right. Okay. Then what happens?
You're on mute, Mr. Bible.
Mr. Bywater, you're on mute. We can't hear you.
Oh, that is amazing. Okay, so not only does it kick me off, it doesn't want me to speak either. Okay. All right, perfect. So Neve, what did you decide was happening here?
In terms of like a, it turns around and goes the other way.
Yeah, it had a positive direction, and then at some point that positive changes to a negative velocity, which just means that it turns around and goes the other direction. Awesome. We know that because positive velocity means to the right, negative velocity means to the left. That gives us the direction. So definitely turned around. Okay, anything else? Anything else you guys got from this?
Yeah, we said that when it changes direction and the velocity becomes negative, it's also moving at a slower velocity.
And why would you say that?
Because the first line is a greater distance above the x-axis than the second line is below the x-axis. So the magnitude of the velocity is greater in the first line than it is in the second line.
Everybody see that? The how high it is, right? It has a higher magnitude here than this one right here, which means it's going faster when it's going to the right. And then when it turns around, it's going a little bit slower. Perfect. Perfect. Awesome. Great. Anything else anybody wants to add?
Yeah, I want to ask, so how would you be able to maintain the same velocity but change directions? You would draw that on the opposite quadrant, to the upper right quad. You'd draw on the upper left quadrant.
No, just like this right here. Right? The distance, how far, right? The magnitude of the velocity is how high it is on the y-axis, right? So for example, in my drawing, I've made this a plus 5 meters per second, which means I'm going 5 meters a second to the right. Okay, this guy down here is at -5, which means he is now -5 meters per second. So up here, he's going at 5 meters a second to the right, and then
Right,
here,
okay.
he's going 5 meters a second to the left.
Yeah.
Yeah, good question. Anybody else?
Mr. Bywater.
Yeah.
Could you do like show this like bottom graph, like compare it to like a position and time graph? Because like I'm still confused on like how the velocity stuff works. Like
Okay. So yeah, so that's a good idea. Let's take this bottom graph. Okay. And can we draw that the same exact thing that's happening here, but draw that as a displacement versus time graph? What would this guy look like if it was displacement versus time? Telling exactly the same story, going 5 meters per second to the right, and then turning around and going 5 meters a second to the left. I'll give you a minute to think about it, and then we'll see if we can put it together. All right, what do you guys think? How would I draw this first part here? The velocity is 5 meters per second. What would that look like in my position versus time graph? Avery.
You just have a line going like up with a velocity of 5 meters per second.
Okay, good. Do I know where it should start?
Yeah, no. Wait. No, I don't think so.
No, velocity doesn't give us anything about position, does it? Okay, and that's another good thing to recognize, is that if you have a speed or a velocity, that doesn't tell you where you are, right? All that tells you is what you're doing. Okay, position tells you where you are. Velocity tells you where you're going and how fast, and then acceleration tells you how that velocity is changing over time. All right, so Averett's exactly right. We're going to have a positive slope going up. You can start it wherever you want, and just to prove that point, I'm going to start it down here. So I'm going to draw this. Okay, my slope should be 5. okay? Position up, meters over seconds. So it goes up 5 over 1, up 5 over 1, up 5 over 1. Okay? Awesome. Then what happens? Then what happens down here?
It would be the same slope, but like in this direction.
Okay, so the same gradient, just in the negative direction. That's exactly right. Now, if this amount of time is the same as that amount of time, then it should go right back to the same position that it came from. And so here the slope should be -5 meters per second, because the velocity is the slope in a position versus time graph. How's that feel for you, Nav?
Okay, I guess that makes more sense because like I confused the velocity like with position because like the velocity was like flatlined, so I was like, so is the object not moving? And like, you know.
Yep. That's, yeah, exactly. You can have a graph that looks like any of these, but the y-axis can change, right? It could be a displacement graph or a velocity graph or even an acceleration graph. What we have to do is we have to get comfortable with looking at that y-axis and interpreting what is happening here, right? We have to be able to interpret, well, does this slope mean that it's moving up? Or does that slope up mean that the velocity is increasing? Or does it mean the acceleration is increasing? All of those different scenarios could play out depending on what's on the y-axis of that graph. And so you have to keep looking and thinking, interpreting what does this mean in terms of what the graph is. Okay, ready for another one? I'm going to send you out into the groups again. Okay, it'll be different groups this time. Hopefully. Okay, here's your graph. Everybody got it? You got 1 minute. Again, we're going to stick with positive is moving to the right, negative is moving to the left, just to simplify. See y'all shortly. All right, welcome back. All right, Elysium, what do you think? Oh, she's got to go to the door. Go ahead. All right. Elena, what's up, dude? What you got?
The object is slowing down.
Okay, why do you say that?
Because the velocity is getting smaller and smaller and smaller.
Okay. What happens right here?
It turns from right to left, changes direction.
What's its velocity there? Sorry, I'm with Elena still. Elena, how fast is it going there?
0. Like it stops and then it turns around.
Okay. How do I know it turns around?
Well, because when you get to the negative part, you know how like -1 is bigger than -3? It's like it speeds up a bit and then it slows down again. So it's probably turned around at some point.
Okay, but how do I know it's turned around? What tells me that it's turned around?
Negative velocity. It's like you're throwing a ball and then it like reaches a speed where it's 0 and then it goes back down.
Right. Elena, what tells me the direction?
The positive and negative parts
Yeah.
of it.
Yeah, so all the stuff up here is positive velocities, right? Which means all of these things up here, it's moving to the right. What about all this stuff down here?
It's negative velocities.
Negative velocities, that's right. They're all negative velocities, which means it's moving to the
left.
Okay, now back to the original statement. Is it slowing down here?
Okay. Yes.
Let's think about this. Let's just throw some numbers in. I threw some hashtags, some tags in there.
Change in velocity of
So let's say that that's a -4, right? I go down a little bit further. Now it's going -8. I go down a little bit further. Now it's going -12. What's happening to the numbers?
They're getting bigger.
Tell me about the magnitude of the numbers.
Oh, well. Frick, what? It's they're getting bigger. The magnitude is getting bigger, right?
Yeah. So what does that mean about the speed?
It's speeding up instead.
Lucia, you want to chime in?
Yeah, I was saying that I found it easier to visualize this as like throwing a ball up in the air. So it's slowing down because the acceleration is in the opposite direction. And then when it switches direction, the acceleration is working in the same direction as the velocity. So it speeds up in the opposite direction.
Okay, all right. So this adds in another piece of what we've been talking about, right? We talked about the slope of the position versus time graph, okay? But what about here? What do I get if I find the slope of a velocity graph? right? Remember, the slope is the rise over the run, or the change in y over the change in x. Y is velocity, so that's the change in velocity over x, which is time. What is the slope of a velocity graph?
Acceleration.
It's acceleration, isn't it? And we have a negative slope here, right? So what that means is that we have a negative acceleration, right? So a negative acceleration, which means when the velocity is positive, negative acceleration means slowing down. When the velocity is negative, negative acceleration means speeding up. If the acceleration is in the same direction as the velocity, it's speeding up. And so that then connects with everything that we've done. All right. So I know it's time to go. So I want you guys to think about for next class, we talked about the slope here. I want you to think about what does the area between the graph and the x-axis represent, and we'll talk about that next class. All right. Okay, you guys did a great job today. We'll continue it next time on Tuesday.
Bye, Mr. Bywater.
Thank you.
Thanks, everybody.
Thank you.
See you, Mr. Bywater.
Thank you.
All right, bye guys.
Now it's just you.
Now it's just me.